and he thought that he had found a three-dimensional representation. So it's a three-dimensional map, not two dimensions, of all of the relations between all of the colors he was aware of. This diagram is imperfect so far as the colors go. I recreated it on my computer, and it came out well enough. You can see what's intended. Yellow is opposite blue, green is opposite red, and white at the top is opposite black, and middle gray is right in the middle of the solid. And all of the other colors radiate out from that central point in a way that you can see, light towards the top and dark towards the bottom. This is how things remain for a long time. What I want to address is a fairly recent theory. Fairly recent. I think the paper was published in 1981 by Mr. Hurvich, and he had working with him a lady, I forget her first name, Jamison, and she did much of the important work. So it's usually called the Hurvich-Jamison theory of how color is coded inside the human brain. And indeed, inside, I think, mammals that have color vision generally. No, that's not quite right. Animal color vision often differs substantially from human. So think of this as primarily a human-directed story. Now we're looking inwards. We're not looking at colors on the outside. We're looking at, well, there's going to be an argument about this. Are we looking at the qualitative character of color sensations in human, or are we looking at the range of possible coding vectors or coding patterns across the retina? That's going to be something we'll talk about after I give you the theory. You can see the explanatory target. If we see that, as we can, as being a map of the range, not of external colors anymore, but as a map of the range of internal color sensations, then you can see that this represents something of interest to us. At the very least, we want to know, how is it possible for a creature to comprehend that range of possible internal representations? And the answer to that question is the Hurvich-Jamison theory. Could I have the next slide, please? Yes, there it is. Now, what you're looking at are two things. On top is the basic and very simple neural network that's supposed to do the work here. And underneath you see a representation of three curves in the optical window from left to right. Blue will be to the left and red will be to the right. And the three curves there represent the sensitivity range of the three kinds of color receptors, or cones, in the human retina. You have rods that are indifferently sensitive to wavelengths. Think of them as the black-white cells, if you like, or dark light cells. And the cones are different. They are differentially sensitive to certain wavelengths. Now, they're not sensitive to a very narrow spike. They're sensitive to a fairly broad range. So they're rather broadly tuned, but they're still sensitive to different wavelengths. There's the long wavelengths, the one with the red tip. There's the medium, that's the one with the, is it a yellow? Or yellow. And then there's the cone that's sensitive to the very short wavelengths, and we've coded that one blue. Now, what these three cells do is simply to register the relative strength, as insofar as they can get it, because they're very broadly tuned, strength of the incoming light at those three wavelengths. Now, The next layer in the network, which is at the very top, is where you get what are called the color opponent cells. And here you have, this is the way to think of it, a tug of war between pairs of cones. The short and the middle both project up to what are called the blue-yellow opponent cell, and those three cells at the top share the following feature in common. They are always active if they're left on their own, if they're free of stimulation or inhibition from below. They're always active at about 50% of their possible level, and in fact that's about 50 hertz per second spiking frequency. They can be pushed down. For example, if you look at the leftmost color opponent cell, the blue-yellow cell, you can see that it has two kinds of inputs. The leftmost one has got a minus by it, and that means that that's an inhibitory connection. If the cell below, the blue one, is actively stimulated, that will tend to push the activation level of that color opponent cell down in the direction of 0, away from 50 and down towards 0. On the other hand, if it gets a stimulation from either or both of the medium or long wavelengths, you can see that there's a plus sign by the connection there. That's an excitatory connection, and that will tend to raise the cell's activation level above 50%, from 50 hertz to 60, 70, 80, to a maximum of about 100 hertz. And there's a tug of war between the blue cone on the one hand and the united pair of the yellow and the red on the other for control of that color opponent cell. Take it above 50%. No, take it below 50%. And you can see that whatever the balance is of stimulation coming from outside, to stimulate the cones, you will get, if they balance perfectly, the opponent cell will simply stay at 50, where it was to begin with. But if there's an imbalance, it will go either up or down accordingly. Now go to the middle opponent cell, and the story here is exactly the same. Indeed, it's even simpler because it only gets inputs from the yellow cone and the red cone, so-called. And once again, it's a tug of war, and it wants to be at 50% if it's left alone, no stimulation from the outside, and it will go up if it's stimulated, and it will go down if it's overall inhibited, and so forth. Finally, the one on the extreme right, this is the white versus black or dark versus light cell. This one is a little bit different. It gets a stimulation, a positive stimulation, you can see from the plus there, from all three of the cones at a particular area in the retina. Now, what's important here, or what's different here, is that the inhibitory inputs to the black-white opponent process cell come from the area immediately surrounding the cells where the cones are located. What we're talking about here is coding a particular tiny portion of the visual field. And this is a center surround cell, and what it's interested in is the relative difference between the brightness at the critical point, the point where the three cones are, and how bright it is relative to the immediate surround. And the immediate surround cells are what send a inhibitory stimulation. Now, what you're going to get when you look at any different color, of course, is a certain pattern of stimulations across the cone cells. And that pattern is going to be transformed via this three-dimensional tug of war, hence the term opponent cells, because they're the tug of war is between opponent stimulations or inhibitions from the retina. You get a pattern across the cones, and that's transformed into an interestingly different pattern across the opponent cells. And that is the pattern that turns out to correspond very closely to the dimensions of color sensitivity that we have. I think I want the next slide at this moment. But remember the color opponent cells. And yes, here I've given you 6 cases. Look at the first, the upper left. If you look at a black object, then the two opponent cells on the left, the blue versus yellow and the green versus red, won't be seeing anything with a chromatic aspect to it. You're looking at black after all. And so they just stay at 50%. But the extreme right-hand one gets a strongly, if you're looking at black, it's a strongly inhibitory stimulation, and so it goes down. And you can see there's like a bar graph with 3 bars in it, and that particular pattern is the pattern of activation that will be produced at the opponent cell population for that little tiny part of their visual field when you look at black. When you look at gray, things change. Gray, of course, doesn't have a chromatic aspect either, but gray is a good bit lighter than black, and so when you look to the, this is the middle bar graph now, all 3 of the cells are just humming along at 50%. And that corresponds to looking at something that is gray. To complete the exploration of this dimension, which is the vertical dimension of the color solid, if you're looking at white, once again, there's no chromatic element in it, but there is a vivid contrast at the black-white opponent cell, and there it's a maximal excitation, and so that little triplet, that threesome of excitation levels, is what will happen when you look at something that's white. To get into the chromatic realm, go down to the lower left where we're looking at something that represents looking at red. If it's a medium red, for example, then what you've got is ho-hum, nothing much happening on the blue-yellow input, but there's a major stimulation on the middle bar, and ho-hum, not very much happening because this is just a middle-level red. It's not really, really light. It's not really, really dark. And so you get that triplet there. It's middle bar is the one that's highest. It's a 0, I beg your pardon, it's a 50-150 activation vector. And the opposite of red being green, I'm sorry, here the camera was the victim of a reflection, I think, through the window. So it's a little bit messed up. That's just the opposite of what we got with red. The middle bar has been inhibited dramatically, and that's what happens when you see green. In the case of pink, that'll be like red, except that the black-white is going to be higher, and you can see that there's a triplet there. 50, 75, 75 is what you'll get for pink. Now, the interesting thing about the coding vectors, the coding triplets that result from the processing of this very simple little network is that all of the colors in the range of possible colors correspond to a particular activation triplet, a threesome on the bar there. And when you map the space of possible activation triplets across the Hurvich Jamison network, you get a map which I think I want the next slide if that's possible. I think I want the next one. Yes, turns out to be a 3-dimensional space because we've got 3 bars, and white is being coded at the top and black at the bottom, and you'll notice that the similarity to the textbook spindle that I showed you here is actually quite striking. In fact, the result from looking at how the neurons behave according to Hurvich and Jamison, is closer to the original Munsell drawing, which I don't have, I'm afraid, than the textbook spindle, which is a bit of an idealization. But here you can see there's an isomorphism in the space of possible activation triplets. That's what you're looking at here. And I've color-coded them according to the kind of color sensation you would have if you were looking at the relevant color. So that you can see that there's a systematic correspondence between the coding vectors in these cells. Now, these cells have been identified in the human brain. We actually find them at more places than we thought we would, but it seems to be the V4, visual cortex area V4, that is especially highly populated with these opponent process cells. You put in on an electrode and you record their activity as you show them blue and green, and they go up and down. And then the one next door, immediately next door, is a blue-yellow cell, and it goes up for yellow and down for blue. And the one immediately next door to both is the black-white cell, and so on and so forth. And V4 is just full of these color opponent cells. But apparently you find them, or cells rather like them, as early as the late stages of the retina. The retina, of course, is itself a multi-layered network. So I can't pretend that there's just one place where they occur. But all of this is of interest to us as philosophers worried about qualia, because what we have found, suppose that Hurvich and Jamison are right in the wiring of the relevant nervous system for color in humans. What we found is a mechanism for coding different kinds of sensory inputs in a systematic way that reproduces nicely their similarity and differences, qualitatively speaking. Now, as I said, originally Munsell was concerned with objective color. But we're here looking at an internal coding, and one might be tempted to say, oh my gosh, here we're looking at the sensations themselves, and we can see how the information they contain corresponds to what's going on in the external world, and we can see how the structure of similarity and different relations between the sensations themselves, if you think of the sensations as being the activation triplet, you need not, of course. This is the question of whether or not we want to be identity theorists or identify qualia with something physical. But if you want to identify them, you at least have the comfort of saying, we've found the right correspondences. This kind of discovery that the space of possible opponent cell triplets reconstructs to a perfection the range of possible color sensations is, of course, perhaps the principal motivation for suggesting that human visual color sensations just are at any point in the visual field, or on the retina, or in the visual field is the way to put it, are identical with activation triplets across the opponent cells. This is the major motivation for suggesting that. The theory itself, I think, is pretty robustly verified. It came out in 81, and that's now 33 years ago, so it's surviving nicely. And it has the virtue, a further virtue, aside from the virtue of getting a nice corresponding structure, it has the further virtue of explaining something about human afterimages. You probably already know that if you stare at a bright light for, well, if it's a bright light, you don't need to stare very long, and then look at a uniform gray surface, you will see a black or a dark afterimage of the bright light you were looking at. You may also appreciate, yes?
Let's get some questions now. I think.
Okay, you want me to get back to the afterimage stuff? Because that's terribly important for the virtues of the view, but perhaps I should stop here.
I think maybe they know that. I mean, I think.
Oh, no, they don't. They don't know what I'm about to tell them.
No.
Tell us, please. No. Okay. The point is this. The theory entails that if you look at something red and produce the corresponding activation vector by pushing the cells away from the 50% level where they want to be, they will slowly get fatigued and they will fall back towards 50-50-50. The system itself is subject to fatigue and or potentiation. If you push something down towards zero, it's not using up the energy it has as quickly, and it builds up and it builds up, and slowly the activation level climbs back towards 50%. So there's this intrinsic tendency to fatigue when you look at a particular stimulus. Now, what happens then when you've got a fatigued system? It's not a normal neural network anymore. It's fatigued and or it's potentiated. If you then look at a neutral surface, like gray of some sort, you will see as an afterimage the color on exactly the opposite side of the color spindle. Anywhere you look throughout the whole outer surface, if you stare at that color and then look at a neutral surface, you will get an after image on exactly the opposite side of the color spindle. And this, I think, is widely appreciated by people, and it struck me as an interesting test of the theory, which turns out to be very good. Black objects give you white after images, red objects give you green after images, yellow objects give you blue after images, and so forth across the whole thing. I will end by pointing out one further feature of this theory, which I stumbled across. You can give somebody a fatigued system by looking at red, for example, for a long time, by which I mean 30 seconds or 45 seconds, not terribly long. The system fatigues fairly quickly. And then have them relocate their vision, not on a neutral gray surface, but say on a black surface. And what happens then? Well, given the fatigue that you've got, the activation vector that results can't be inside the solid. It's got to be outside the solid in the space of possible activation vectors that will not be produced by anything in the external world. If you look at red for a long time and then look at a black surface, you will see a weird after image of whatever it was you were looking at. Suppose it was just a circle. And you will see the prediction is, well, it's got to be the opposite of red, so it's got to be a green of some kind. But how can it be green if you're looking at black? What you get, in fact, is an after image that is as black as the darkest possible black, but is still distinctly green in some unfamiliar way. It's a weird qualia you've probably never had before, or if you did, it was an accident and you didn't notice. That turns out to be true across the board. If you look at yellow for a long time and then relocate your view on a black surface, you get a blue of some weird kind you've never seen before. It seems as dark as the darkest possible black, but it's not black. It's somehow strangely bluish in some unfamiliar way. And finally, if you fatigue on any color you like, say on red again, and then you look at a bright white surface, you will notice if you're fatiguing on red, you will notice a greenish after image, but it's as if it were self-luminous. It's as if it's a neon light. It's brighter than the white that you are looking at. And that is what the theory predicts as well. That's why I call these chimerical colors and named the paper after the chimerical colors. And I hadn't seen anywhere in the literature that this was a consequence of the theory, but it is. And if you test it out, you get these chimerical phenomena. And as I was explaining to David at the bar the other night, when I stumbled upon this was 10 or 12 or 15 years ago, I thought, my God, we're here producing phenomenal qualia that I've never had before, that I'm not even sure they exist. When I look at them, they look so weird and strange and unfamiliar. And what we've got is a prediction from a physical theory of a phenomenological quality that, like Mary, I had never counted before. And so we had a nice little discussion over our Chardonnays or whatever it was about what the significance of that was. And I'm not sure what lessons we should draw from this. David wants to draw some slightly different ones. But this is the story that is now standard fare in psychology concerning how the human visual system codes color information. Now, whether you want to take a deep breath and say, we've discovered what color sensations are, they're activation triplets across the opponent cells in your brain area V4, which is what I'm tempted to do, or whether you want to say something else, perhaps we can discuss. But now at least you know what the fuss is about. Thank you, guys. Yeah, I'll be happy to take questions, and if you don't have any questions, I will quite understand. Yes?
as I know, we nowadays know a lot about the mechanism of vision of some animals, mammals.
Yes.
So can we say that we do know something about the qualitative stage?
Well, I'm tempted to say yes. And I'm not sure what David would say, but I'm committed to saying yes, I think. If color coding in the other animals is the same as ours, or even if it's interestingly different, if they have 5 kinds of cones and 4 kinds of opponent process cells, we can at least put together a map of what the range of possible color sensations for them would be, and you'd be making a prediction about what kind of qualitative character they'd be having. Whether they're an identity, of course, is a matter of how impressed you are by the systematic parallels discovered between phenomenal quality as reported by normal humans and coding vectors as postulated by the Hurvich Jamison theory. I should add also that if you destroy one of the 3 kinds of opponent cells, disable them, say the red-green one, then you've got somebody who has a reduced color space. They can see the differences between blue and yellow, but they cannot see differences between red and green. And there are, of course, people who are red-green colorblind, who are blue-yellow colorblind. It turns out they divide up in this way, which is what you'd expect if that theory were true, and there was a specific deficit in one of the pathways from the retina to the opponent cells, or if you didn't have one of the relevant kinds of conal cells, you would get a deficit, even if the wiring were there. It wouldn't be functioning normally, and you could predict how it would misbehave. And the people who have these kinds of color blindness show those kinds of deficits. So the theory does well there too. I'm inclined to think the theory is true on the basis of all of this. Whether or not it justifies the claim of an intertheoretic reduction is something we philosophers can talk about. That is at least a second issue. When you look at other animals, yeah, some of them have deeper color penetration than we do. Dogs, for example, have poorer color vision than we do. It used to be thought that dogs were colorblind. Not so. They just have only 1 kind of cone or only 2 kinds of cones, where we have 3. So here is a way to probe the differences between the perceptual capability of humans versus dogs versus other animals, other mammals, and so forth.
I know some
pigeons.
Say again?
You might mention pigeons who have 4.
Do pigeons have 4 kinds of cones? Then presumably they have more well, it's also claimed, I should say, that some humans have a 4th kind of retinal cone cell. And there you want to wonder, do they still have the same population of opponent process cells? You just got a finer grained first layer? I don't know the answer to that. I think it's only females, humans, who have the extra kind of cone. And they apparently do see things slightly different than the rest of us, as is well known. Yeah, those details I don't know, but they intrigue me too. Yes, Andy?
So a different kind of question there. Do you think there's a kind of point along these continuums where experience starts to happen or not? So if I had a very quite simple version of this, which you probably could have in a little robot or something, would you like to say, okay, there's a little bit of qualitative experience because it's a little tiny
a simpler version in this camp.
Yeah, so some question somewhere in that ballpark, you know, is an implication of taking this as a good theory of qualitative experience, that qualitative experience is a kind of continuum all the way down to stuff that perhaps currently we don't recognize?
I'm inclined to say yes. That would seem to be the reasonable way to go. I'm not quite sure what the consequences of that would be. I think it's important to note that while children at age 2 or 3 who are now using the color vocabulary. It takes them a while to get there. They're using it. They are not yet talking about sensations. They are not yet talking about the qualities of their sensations. That's not a vocabulary or a dimension of discussion that they have ascended to yet. But I'm inclined to think that sensations exist, and I want to understand them too. And I'm inclined to agree with everybody that they have qualitative features, but I'm not quite
Children will discriminate, make the same discriminations on the Ishihara color blindness test. They have the capacity to make the discriminations long before they can name them.
Indeed, and long before they can make self-conscious announcements about the content of their experience. That's a skill they learn later on. And I'm not sure what happens to brains when they learn to do that. I'm inclined to think that I want to disagree with Dan on his principle of no double transductions. I know the motivations Dan has, which is to escape the homunculus, who is the seat of the second transduction, and that's a perfectly legitimate motive. But as I look at the brain as a hierarchical neural network, there's the first transduction and the second and the third and the fourth and the fifth. In no case is there a homunculus sitting behind any of these transductions, but
I would call those translations, because you're still in the medium of spike trains. You're just recoding. It's not transduction when you have the same levels in a computer, which you can have. In a computer vision system, you've got the same sequence of recodings in effect, and they're not transductions. It's bit streams all the way.
Although there's, I think in the hierarchical models there, it is true that for every level above treats the level below as if it were sensory evidence.
Yeah,
in
yeah,
effect.
yeah,
So in that sense.
that's right.
Yeah, yeah.
And interprets it in terms of its acquired categories.
Yeah, but to me, the important point is it's bit streams all the way in the computer, and it's spike trains all the way in the brain.
So you never develop the film in a way and get back to the color.
Right.
You never escape the domain of physical coding. Oh, I agree. That's why I want to be an identity theorist about this. It's not that you change to some different kind of representation.
That's why I don't like you using the word transduction. I take transduction to be the rods and cones are transducers. But what happens next is not transduction.
Well, surely not much hangs on whether we use the word transduction or translation. We'll talk about this over Chardonnay. David, you've been patient.
Oh, I just wanted to hear the just following up on Andy's question. Then I take it that if we use this model to build an isolated opponent process model in, say, a camera, you'll be very happy to say that it does in fact have color experiences.
Well, as an identity theorist, that should be, strictly speaking, what I would say. But as Dan has pointed out to me on other occasions, one of the problems with being a strict identity theorist is that you ignore the enormous surround in which the particular things are embedded. And since we both agree that consciousness has an important integrative component, that larger surround is going to be important. I'm not eager to ascribe phenomenal qualia to cameras, David, you'll be pleased to hear. Okay, you'll be disappointed to hear.
But David at least thinks the camera is proto-conscious.
But if we get a bigger story of what's going on in the brain at large, and we see these opponent process vectors in the context of the larger system, the idea that they embody phenomenal properties may not seem so strange or weird or arbitrary.
It's all the answers to the "and then what happens" questions.
Sure. But you need the beginning.
Oh yeah.
And here I think we have some rather exciting encouragement for proceeding along those lines to see how well it goes.
So you don't really then have an identity between color experience and this narrow coding property. Rather, that's a very partial realization.
I understand the motivation for that remark, and part of me wants to say you're right, but Let me think about that. I'm not sure what's the best response to you, dialectically speaking. You know, what trouble am I going to get into?
This isn't the response which particularly turns on physicalism versus dualism or whatever it strikes me. It seems that, I mean, a functionalist, as Dan says, is going to say, well, what's really doing an enormous amount of the work is the stuff downstream from here.
Yeah, and I'm inclined to agree with that.
Yeah, cut the optic nerve in somebody, and they've still got the opponent cells doing this coding and translating it just so far, but then nothing else happens beyond that. And that's so.
Not clear. I was suggesting early on that the opponent process cells are in V4. But
yeah, but there's also, well, actually, when the fact that the cell in V4 shows this property, it could just simply be a straight through line to the retina.
It could be. It could be. Yes. Yes. I don't know that it's not.
Paul, do you remember at Francis Crick's tea when this issue came up? And Francis was taking the line that you're still clinging to somewhat gingerly at this point. And I said, you mean if you had those V4 cells in a Petri dish stimulated, there would be an experience of red in the dish? And he bit the bullet and said, yes.
Oh, wow.
Well, that says something about Francis Crick.
And I'm suggesting you don't want to bite that bullet.
I'm suggesting I'm wary of biting that bullet too. Yeah. Yeah, I'm. We probably need to move on. Yes, you now at least know what the HJ account is and how perhaps it bears upon the philosophical issues that concern all of us. Thank you for listening.
Beautiful presentation.